Hi, this is Rohan from educator.ai. Let's dive in. Welcome. Today we build the retrieval half of RAG, the part that finds the right text to hand your model. By the end, you'll be able to review a pull request and spot where retrieval quietly breaks an answer. Here's the situation. You have a mountain of documentation, but the model's context window only holds a few pages. You can't paste everything. And plain keyword search fails the moment a user asks in different words. We need a way to find text by meaning, not by exact spelling. Think of a library where books aren't sorted alphabetically but by what they're about. Books on similar topics sit near each other. To answer a question, you walk to the region it belongs to and grab the closest books. Vector search is exactly this, a map of meaning where nearness means relevance. So how do we build that map? First, text becomes tokens, small pieces with integer IDs. Then, an embedding model turns a whole chunk of text into one list of numbers, a vector. That vector is a point in a high-dimensional space where direction encodes meaning. Let's build the space one step at a time. Here are three billing terms: refund, return, chargeback. Because they mean similar things, the model places them close together. Proximity is the whole point. Distance on this map is distance in meaning. Now add a second topic, login, password, two-factor auth. This cluster lands far from the billing cluster. The model has never been told these are separate categories. The separation emerges from meaning. Unrelated ideas simply point in different directions. One subtlety. We usually care about the direction a vector points, not how long it is. Cosine similarity measures the angle between two vectors. 1 when they point the same way, 0 when unrelated. Same direction means same meaning, and that's the number we'll rank by. Now the trick that makes it all work, we embed the user's question with the very same model. The phrase "get my money back" never uses the word refund, yet it lands right inside the billing cluster. Query and chunks share one space, that's the non-negotiable rule. We sort every chunk by cosine similarity to the query and keep the top few, the top k. Here k is 2, so we pull in return and refund. Those become the context we feed the model. Choosing k is a real decision. Too small and you miss the answer. Too large and you waste tokens and money. Comparing the query against every vector works for a few thousand chunks, but not millions. So vector databases use approximate nearest neighbor search, an index that navigates toward the right region without checking everything. You trade a tiny bit of recall for enormous speed. That's the engine inside tools like FAIS or a managed vector store. Let's confirm the mechanism in code. We embed a query and three chunks as small vectors, then score each with cosine similarity. Notice the billing chunks rise to the top, while reset password sinks to nearly 0. This ranking is exactly what a vector database does, just with far more dimensions and far more chunks. Here's how it looks in production. Embed the question with the same model used for the chunks, search the index for the top 4, and stitch those into a grounded prompt that says, answer only from context. In a pull request, check three things: same embedding model, a bounded k, and a prompt that pins the answer to retrieve text. The single most important idea for reviewers: retrieval quality caps, final answer quality. If the right chunk never gets fetched, no amount of clever prompting saves you. The model literally cannot cite text it never received. When answers go wrong, inspect what was retrieved before you blame the model. A few traps recur constantly. Embedding the query with a different model than the documents puts them in incompatible spaces. Everything looks unrelated. Chunks that are too big blur many topics into one vector. Too small, and they lose context. And blindly stuffing every hit, even weak ones, floods the prompt with noise and cost. Here's your checklist for the pull request. On the left, healthy retrieval. One consistent embedding model, a bounded k with a similarity flow, chunks sized to a single idea, and an eval that measures whether the right chunk was actually retrieved. On the right, the red flags to block: mismatched models, unbounded context, blurry mega chunks, and no evaluation at all. To recap, query and chunks live in one shared embedding space. We rank by cosine similarity and keep a bounded top k. Approximate nearest neighbor indexes make that fast at scale. And above all, retrieval quality sets the ceiling on your answer, so review the fetched chunks first. Nail retrieval, and grounding does the rest.